Good day viewers, thanks for joining me for this video. We continue our series that we've been working on, taking on this particular project sample. If you are seeing this video for the first time, I would implore you to go and watch my previous video when we started this series. So the last where we stopped was the slab classification, and I made this Excel sheet for our slabs, and I took some slabs that will be designing manually out of the slab arrangements that we made. So I took sample from the slab types that we have. So I have it here. So I have also made some free body diagram for the representation of this our slab for analysis sake. So, and I have, if you look here, I have compute the design load, then design point load, as we have cantilever in our model. So I'll start with the first slab type 4, which is spanning 3 meters, and this is the length. So the slab type 4 is a representative of other slab type 4 that we have in our layout. So, and I took this slab type 4 spanning 3 meters, then this is 9 meters, and that is what we have here. So it's a one-way slab. Now this is the design load that I compute based on the normal formula for design load. And like I said, if you have not seen the previous video, then you have to go back to my YouTube channel and check the previous video where we have all these parameter, and that's how we came about the design load that will be on the slab. Computing using the dead load and the imposed floor load, which is gotten from the code, and that's how we arrive at this design load 18.08. That's 1.4 by 7.2 plus 1.6 by 5. 7.2 is the total floor slab load that we have here, where we compute our load, and this is the point load on cantilever slab, and this is the imposed floor load, and that's how we got our design load. So our design load will be uniform for all the slabs, and that's what we have on all the slabs type that we have taken as our sample that we will design. Then I also have design point load, so which means the wall load that will be coming on the edge of the cantilever. So this is the load multiplying the unit weight of wall by the height of wall, and that's what we have here. So then I'll multiply it by a factor of safety of 1.4. So now not all the slabs have point load, so that's why you see new. So it's only on this slab that we have this point load, this cantilever slab, which is spanning 1.98, that we have the point load, this cantilever and this cantilever as well. That's where we have all the wall load when we get to the upper floor based on these arrangements. So these are the wall load that is sitting on this cantilever slab on this floor. So that's why we have it. Now if you look at the other cantilever slab, which is spanning 0.9 meters, there's no wall load sitting on them. So this is it. There's no direct wall load sitting on them, even though we have a wall load that is sitting on the edge from the architectural arrangement. These are the walls, these walls that serve as aesthetic. So in my model, which is this, so the wall load, I've I've assumed that since I've factored the load, then I didn't consider that because the effect will be negligible. So I did not put wall load on that slab. So that's why we have it here. So that's why it's nil also in this case. So every other slabs, I've assumed partition wall allowance on all those slabs. Now this is the arrangement of the slab. Now when we take slab type 4 now, is spanning 3 meters. So this is a representation. Now for if I am designing manually and for one way slab, I know that if I'm taking the slab one by one apart, so I'm assuming that I'm taking this slab away from this model, then I have something like this. Then the normal formula that we have is WL square over 8, which will give me the maximum span moment. And this is the maximum span moment based on this formula, which is 20.38. Now, but mind you, I am constructing, I have other adjoining slab that forms a kind of restraint for this particular slab, which means that this particular slab that I'm taking as a text, that I'm taking as a representative for design, is not standing alone. It's have adjoining slab on all the 4 sides. So by that, I can use this formula recommended in the code, BS code, BS 8110. This is it. So bending, you can see bending moment coefficient for slab spanning in 2 directions at right angle, simply supported on the 4 edges. So I can safely use this coefficient based on what the code said when it comes to simply supported slabs. So if this particular slab is isolated, then I can use this maximum bending moment, which assume that there's no moment here, there's no moment here. But in my actual case, there's other slabs adjoining, so that means there's a restraint. Then I will have top bars along all these edges. So in that case, I will have support moment in that case. So in this case now, the using this formula recommended in the code, which is this, then my moment is 10.10. Then when it now comes to the support, I can assume the same moment to design the support reinforcement and check it with the minimum area of reinforcement required. Whichever one is higher, then I will use it to design for the support reinforcement that will go along this line into the adjoining slab. In that case, which means that my span moment will be reduced, which is what we have here, compared to if I assume that this slab is standing alone and is not adjoining into any other slab, then I use this as my moment, WS square over 8. So these are the two moments gotten from that. Then I go to panel 1 now. Now panel 1 is a two-way slab, and panel 1 and slab type 2, panel 2, if you check very well, I will almost get the same thing. So I only made uh, the moment for only slab type 1, because checking it, you will discover that you will get the same coefficient, moment coefficient for, because they are both interior panels. So I only compute the moment for slab panel 1, and this is it. The case is interior panel, and from the code, which is table 3.14 interior panel, this is where I got the value from long span coefficient. Now in this panel also, you will notice that both dimensions on the panel, they are same, 6 meters, 6 meters. So in this case, there's no clear distinction between which one is the short panel, which one is the long panel. So I took the liberty and assumed that, okay, both of them are long span, and that's where I got the coefficient for support, the negative moment, and the coefficient for the positive moment that you are seeing here. So for short span coefficient is same, for long span coefficient is same. That's because there's no distinction with which one is the long span. But if I want to do like short panel, then I have to do an y over lx, which will be 6 meters divided by 6 meters, which will fall in this category. And you can clearly see that the coefficient of the positive span moment is same as we have here in the long span coefficient. So the negative moment is also not too very far from each other, 3.1, 3.2 in this case. So I settled for this, representing that since it is both 6 meters, then I use the same coefficient, which is not very far from each other. So that's how I got the moment here. And you can see from the code, this is the formula that you will use to get your bending moment in that place for this slab. So this is the formula to get the bending moment. So I've calculated that. So for short span, span moment is this, then continuous edge, which is the negative moment, is this. And by that, since it's the same coefficient, I'm going by the design load that is coming on it. So it will be same in this case. So like I said, this slab type 2 and slab type 1 are same because both of them are interior panel. So they will have the same, and they have the same dimensions as well. So it's the same thing that you have here, you will have here. So I did not put that. Then we'll now go to slab type 3, which is also two-way, but the case is now one long edge is discontinuous. So by that, the coefficient also is different. Then again, you can see the dimension are also the same. So I also used the long span coefficient for both the long span and the short span. In that case, you can see that one long edge short discontinuous. This is the case of that, which is case 3, 0.03 and 0.228. So if you look at it with the positive movement at, if I'm classifying it as a short span and long span, it is not also not very far from each other. So but since the dimensions are same, so I used this dimension for the long edges to represent for the short span and the long span. And this is what I have here, the short span coefficient and the long span coefficient. Using the same formula, I got the short span moment, and then the continuous edge, long span moment, and then the continuous edge. So what it means is that if you arrange your reinforcement, if we arrange our reinforcement like this, like in this direction, if we arrange our reinforcement in this direction, and we also arrange our reinforcement in this direction, then the continuous edge are the reinforcements that will come at this edge, and same at this edge. So using this movement, span movement for short span will represent one of the dimension, which is, if you consider it in this x direction, then the moment you get here is one you will use to calculate for the reinforcement that will come here. Then the continuous edge will now be the moment that you use to calculate the reinforcement that will come along the edge of the slab. So that's what span and continuous edge means, for clarification's sake, if I have any viewers that does not understand what span and continuous edge means. So that is that for case 3. Then I move on to the cantilever slab 6 and 7. 6 and 7 are both cantilever. The difference is the span that is different. So for 6, I have 1.98 as the span, and for 7, I have 0.9 as the span. Then for cantilever slab type 6, I also have a point load that is acting on it, which is what I have done here for clarification case. But for type 7, there's no point load that is acting on it, based on what I've explained before. So for 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 cantilever type 6, this is the formula I use to get this moment. So the formula for the UDL and the moment for the point load. So with this, I come up with the moment that is coming on this slab. This moment will be used to calculate for the reinforcement. So, and for this one also, with the span, and this is the moment for that as well. So I hope it is clear from here. So it is this moment that is now used to calculate for reinforcement. Now, the aim of this series is to compare what we have manually with what the software gives us, and the software we are probing is prota structure, as we have been talking about over the past videos. So with this, with this that I've done, when we get to go into the software to actually model this same model that we have, then we will now compare the moment gotten from the software and the moment we got here manually. So that is the goal of this series. Okay, and like I've mentioned in my previous video, I've modeled it before one time. So but we'll remodel it when we get to that stage again from scratch. God granting us grace, we'll remodel it from scratch again. So like I said, the aim is to compare what the software gives us with what we have here. And I hope from here on, when you have the moment, you can use that to calculate for the area of reinforcement that will be used for reinforcement purpose, for detailing from here on. So I hope it's clear and it makes sense to someone out there. These are the moments gotten. So we'll use this in comparing with what the software gives us. So in our next video, we'll now decompose these slab loads onto beams. Then we'll get the moment on the beam as well. And we'll make arrangements of the beam arrangement. So like if we have this beam now is a continuous beam that span from here down to here with different intermediate span. So we'll take a sample beam as well and get the load that will come on it and possibly get the moment that is coming. And in turn, when we are done with that, then we'll now go into the software and model the same structure here from scratch, and we'll move on from there. Thanks for joining me for this video. I will see you in the next video. Um, this video might take some time before it comes, before I post, but be assured that I'll finish this series and also talk about some other things that I mentioned earlier when this series started. So it might take maybe like 3 weeks or a month because I'm working on a particular project that is tasking. So I barely have time, and the project is actually out of my base. So please bear with me. But I assure you we'll finish this series by the grace of God. Thanks for joining me. I'll see you in the next video. Bye.